Okay, it is the first day of calculus, and before we get started, I just want to let you know that this first chapter is the author's approach to the three big ideas in calculus. And the three big ideas, let's label this 1-1. The three big ideas are derivatives, limits, and integrals. And in integrals, there's two kinds. There's definite and indefinite. Okay, so in this, like I said, this first chapter, we don't really get into the calculus ways to do these things. He takes a real grassroots, hands-on approach so that you understand what these three things are. And it takes a couple days on each one, but today we're going to be talking about the derivative. And what a derivative is it's an instantaneous rate of change. Instantaneous rate of change. And when we talk rate of change, we're talking about how fast something is changing at a given instant. Okay, and it takes calculus to do this. So the technique we're going to use today is an average rate of change. It will not be an instantaneous. But I'm going to show you a technique that can tell us what the instantaneous rate of change is using an average rate of change. So for us today, we're going to be doing an average rate of change. It won't be the instantaneous. So we're going to first look at a situation and then give an equation for it. And our situation is going to be one of those automatic door openers. You know, when you walk into a building and you hit the button and the door swings open, gives you time to walk in, then it closes automatically behind you. So we're going to examine an automatic door opener. And this is what happens. After you press the button, the door is going to open fast. It's going to slow down as it reaches its maximum opening. It's going to stop for just an instant before it starts closing again. So then it starts closing. And then it's going to slam shut on the very end. So what we're going to do as our two variables, we're going to let the y-axis, the independent variable, that's going to tell us the degree of the opening. So if the door is completely closed, its opening is 0 degrees, 45 degrees, 90 degrees, and if it has room, it may go back to maybe like 120 degrees before it starts shutting again. So the y-axis is going to be the degrees of the opening and then the x-axis will be the time in seconds since you hit the button. And we're just going to make a rough sketch of what this might look like. So here's our time in seconds, and here's our degree of the opening. So obviously the door is starting closed at time 0. Then when you press the button, the first thing, it opens fast. So that means we're going to have somewhat of a steeper line here because the degree opening is going to happen quickly. Then it's going to slow down. It's almost going to stop. And then it starts closing, but it's going to close a little slower so it doesn't hit you as you're going through it. So it's going to be a slower close. And then right near the end, it's going to slam shut, so it'll go quick. So that's just a rough sketch of it. Now we do have an equation that will fit this graph. And the equation is that the degree of the opening, I'll use d for degree, it's our y-axis, is equal to 200 times t, the time in seconds since you press the button, multiplied by 2 raised to the negative t. Okay, well, I want to make this sketch on the calculator so you can see it, and you're going to need your calculator, so go ahead and grab yours. Do the same thing I do. Okay, go into the y equals. Type in that same equation. Get this so you can see it. Maybe. There we are. Okay, 200 x times 2 raised to the negative x. Okay, now if you just hit graph, you may not see anything. Now, you can catch a little bit of the graph over here. And the reason we're not seeing it is the window's not quite right. Remember, on a standard window, this is only going 0 to 10, and this is degrees. So this was only showing me the first 10 degrees of the opening. So we're going to go to Window. And for x is time. And if we think about it, we're going to look at from 0 seconds to 10 seconds. That'll be good. And the y, being the degree, will go from 0 degrees to, say, like I said, maybe 120 degrees. Might be good. We'll see if that's enough. And this y scale is just where it's going to put a tick mark. So because I've got from 0 to 120 and leaving this at 1, that'll put 120 tick marks on that y-axis. That's a little excessive. I think I'm going to change this to every 10. And now let's see what we get. And there's our graph. Very much like what their sketch was. Okay. So now that we have that, now we'll get into some rate of change stuff. So my first question here in this example is how fast is the speed? That's a rate. So anytime you're seeing that phrase, how fast, think rate of change, rate. So how fast is the door moving at 1 second? So that means 1 second after you've pressed the button, how fast is that door moving? So let's think about what we're going to do here. I need to get a rate. Rates are speeds. And if you look at our graph, we can create a speed out of this. This is some physics. I can get how many degrees per second, because those are the two variables I have. So that will be my rate of speed, will be degrees per second. I'll show you how we're going to do that. So the first thing we're going to do is see where the door is at 1 second. And we're going to use the table feature on the calculator. And we'll be doing a lot of stuff on this calculator through the whole year. So I want you to go to Table Set. It's in yellow here, right above this window key. So go Second, Table Set. And I want it to start at 1 second. And then this table increment, it'll count by it because there's a 1 here. It'll go every 1 second after that. And I'll show you what I mean. So now to see the table, you go over here, right above the graph in yellow. So you got to hit the second. So at 1 second, the door's at 100-degree opening. At 2 seconds, the door's at 100-degree opening. At 3 seconds, it's at a 75-degree opening. At 4 seconds, it's at a 50-degree opening. You see it's closing here. So what I know right now, make a little table, time and degree. At 1 second, it's at 100 degrees. So does that mean it's moving 100 degrees per second? I don't think so. That's just where it's at. So what I can do to kind of estimate the rate of change is see where the opening is at just a little bit after 1 second. Let's say like 1.1 seconds. Where is the door at? So the way I can get the calculator to do that is go back to Table Set. Leave it at 1. This time change the increment to 0.1. Now watch when I go back to the table what it shows me. So at 1 second it was at 100. At 1.1 second it's over here at 102.63. And the calculator is very limited in how many decimal places it can show here. But if you arrow over, look at the bottom, you can see the whole value for 1.1. So right now I'm at 102.6336. I'm going to go at least 5 places out on these. So 102.63363 if I round off. Okay, so now what I can do to turn this in to figure out how fast it's moving at 1, and it's just going to be an average because I'm looking at what's happening in this very short interval. And that's going to be my estimate for what's happening at 1 second. And the way we're going to do that is by taking the change in degree over the change in time. So that will give me degrees per second. So when we do the subtracting, it's always the higher time minus the lower time. So to get the average rate of change, it's the change in y values over the change in x values. And to get the change in something, you subtract. So all I'm going to do is take 102.63363 and subtract the 100 degrees, and then do the change in time, 1.1 minus 1. So that will give me 2.63363 divided by 0.1, which will give me moving the decimals over, 26.3363 degrees per second. You will have to label everything. If you don't have labels on your answers when it's a story problem, that will be -1. Okay, that gives me an idea of how fast it's moving at about 26 degrees per second at 1 second. Now we can get more accurate. Like I said, calculus will be able to find the instantaneous rate of change. It will not be the average. But if I can be more accurate by making my increment in here smaller, getting a number closer to 1 as opposed to 1.1. So watch what happens here. I've got the 100 degrees. Now instead of going to 1.1, I want a number closer to 1. I'm going to go with 1.01. That's a whole lot closer to 1 than 1.1 is. So to make the calculator figure this out for me, and really all I'm doing when I use the table, all the table does is it takes these numbers and puts them back into the original equation. It's putting 1 in here and here and cranking through it. Then it put 1.1 in here and crank through it. The table does all of that for us, so we don't have to do all that by hand. So I'm going to go back to table set, leave it at 1. I'll go 1.01. Oops, not that. I'm going to have it jump by 0.01. Now I've got the 1.01 there. And again, you don't want to use 100.3 because the calculator is rounding off. You want to use this big decimal down here, and you want to go out at least 5. Now I'm at 100.30234. Now I do the same rate of change. That's change in y over change in x. So it's 100.30234 minus the 100 divide by 1.01 minus 1. So that will give me 0.30234.01. It's the difference there, moving over 2 places. This time, my rate of change is changing from 26 degrees to about 30.234 degrees per second. So it's a little faster now at 1 second. How can I get more accurate than that? Well, pick your second number even closer to 1. We're going to do this 2 more times. And this time, instead of doing them separately, I'll put them all in one table so you can see what happens to that rate of change. Time and degree. So 1 is 100. This time I want to go with 1.001, and I want to do one more, 1.0001. That will give me 4 values, and we'll see what's happening here. Oh, maybe one more. 1.00001. Okay, so one at a time I'll get these. Table set, 0.001. And again, make sure you get the cursor on the number so you can get all the decimals down here. Don't just use the chopped off decimals here that are in the display. So 100.03064. Doing the next one, changing that to 0.0001. 100.0030. I'm going to go 6.8 there. Carry it a little bit farther. And one more. 0.1234 zeros and a 1. That's this first one. 100.000. And really what you're looking for are, like, not counting the zeros there, you want the 5 values after here. And I only did 4 there, but 3068. Oh, and see, now we're starting to get the same. So I think we're good. So if we do the rate of change between these two, the 1 and the 1.001, and then always back to these two, we'll do rate of change. And then these two will do rate of change. So it's always comparing one to the one that's close to it. So if we do that rate of change on the first one, I'll call it A, B, and C. So A is going to be 100.03064 minus 100 over 1.001 minus 1. Again, very easy to do, so 0.03064, 0.001. So moving everything over 3 places, 30.64 degrees per second. Okay, so let's see what's happening. I went from 26.33 to 30.234 to 30.64. Go again. B, I'm going to be subtracting this one and the 1. So it's 100.003068 minus the 100 over 0.0001, 0.003068, 0001, move everything over 4 places, 30.68 degrees per second. And if you look at C, I think you're going to see we're going to get the same thing we got here. So 100.1233068 minus 100. Oh, I just did the subtracting there, I see. So then 1.00001 minus 1, 0.0003068 over. And if you move everything over 5 places, 1, 2, 3, 4, 5, you're going to see we're going to get that 30.68 degrees per second. And now we've gotten the same thing twice. So what we just found is the limiting value. The closer we get to 1, the closer and closer we get to 30.68. So the average rate of change is about 30.68 degrees per second. Now, because this is a positive value, a positive rate of change, what that means is our independent variable is increasing. So positive rate of change means that the independent variable is increasing. It's bad increasing there. So think about it. Our independent variable was the degree of the opening. If that degree of the opening is increasing, that means our door is opening at 1 second. So it's still on the opening. So this positive value means that the door is still opening at 1 second. And you can see that from the graph. I'll show you. So if we go back to the graph, and if I press the trace, and I press 1, because that means X is 1, I hit enter, it jumps right to that spot. And you can see it's still on the opening. Here's where it stops, and then here's where it starts closing. So I should have gotten a positive rate of change here. And okay, I want to do one more with this problem. So example 2. Well, that's actually, did I call it? It's the same equation. I'll go with B, because that first one's how fast is the door moving at 1 second. So I'll change this to B. How fast is it moving at 4 seconds? How fast, think rate of change. Is the door moving at 4 seconds after you've pressed the button? So we're going to do the same thing. I'm not going to take quite as long to go through it. So we're just going to go with the table with time and the degree of the opening. So 4 seconds is where I'm starting. Let's go with 4.01, 4.001, and 4.0001. So if the book does not tell you the increment to go by, let's go with this 4-step table here, because I can't remember what the problems do. All right, so now we just got to go back and get our table set. Have it start at 4 seconds, and I'll have it do the first one, 0.01. So at 4 seconds, the degree of the opening is 50 degrees. Then at 4.01, again, go out about 5 places, 49.77876. Back to table set. I'll change that increment to the 0.001. Come down, 49.97784. Let's see, that would be 85. And then our last one we get by changing to 0.0001. $49.99778. Okay, so doing the rate of change, again, it's always the higher time value minus the upper time value, or the lower time value. Upper in the table, but lower in value. So it's, when we pair these two up, it's this one minus this one. So for the first one, 49.77876 minus 50 over 4.01 minus 4. I'm just going to set them all up right now. So then it's these two. So 49.97785 minus 50 over 4.001 minus 4. And then the last one, these two, 49.99778 minus 50 over the change in the x's. Okay, now it's just some simple calculator, subtracting and dividing. So if I do the first one, 49.77876 minus 50, I get a negative 0.22124. Divide by 0.01, I'm going to get a negative 22.124 degrees per second. And we'll talk about what that negative means after we're done here. Doing the next one, 49.97785 minus 50, negative 0.02215.001, and then our last one, 49.99778 minus 50, negative 0.0222001. Okay, 3 places, 22.15 degrees per second, negative, and then negative 3 places over, 22.2 degrees per second. So You can see we're very close to negative 22 degrees per second as our average rate of change. And because this is negative now, a negative rate of change means that our y value is decreasing. Negative decreasing, positive increasing. Well, if my degree is decreasing, that means my door is closing. So the door is closing. Okay, so what did I want you to get out of today? I wanted you to be able to find an average rate of change, and I want you to be able to tie that back to the question, how fast, and that rate of change is tied to derivative in calculus. So derivative equates to rate of change. Okay, you made it through your first section of Calc Notes. The homework assignment for this section, which you will work on in class tomorrow, is, let me find it, Calc, page 5, number 1, parts A through D, and number 2.